Hi, my name is Sudeep Dasari, and I'm presenting transformers for one-shot imitation. This is joint work with Abhinav Gupta. Humans can easily visually imitate. For example, if you saw an example of someone taking that red block and placing it on a stack of other blocks, you could easily perform that same task yourself at home. Can we teach robots to do the same? What sort of visual representations are required to make this possible? First, let's define our problem setting. We assume that we have access to hundreds of paired human and robot demonstrations during train time that are loosely grouped by task. To be clear, this task grouping is semantic, and thus the environments don't have to exactly match. During test time, the robot must watch human demonstrations and then generalize to perform new tasks displayed during those representations in its own environment. It must deduce that task from context video and then perform it. We hypothesize that a good visual embedding is sufficient for one-shot imitation learning. The embedding should use context to filter out irrelevant details and focus on what's really needed to do the task. And furthermore, should preserve important dynamics information that's required to make the policy successful. Inspired by recent successes in NLP and vision, we choose to use the Transformers neural network architecture. This is powered by spatiotemporal attention. Human context video frames and robot observations are first passed through a ResNet 18 architecture and then processed further using a transformer attention module. The final result is a per time step embedding where every robot video is filtered using the human context and then turned into an embedding vector. How should this embedding vector be supervised? Since we have access to ground truth actions, a logical choice is to use a behavior cloning loss. However, behavior cloning doesn't always focus on the important details needed for dynamics information required to have a successful policy. Thus, we also add an added inverse modeling loss, which predicts in-between action from subsequent representations. And finally, we add a point loss that predicts where the robot will end up in the future. Our method is experimentally verified in a simulated environment which contains 16 pick-and-place tasks. The red Sawyer robot acts as a stand-in for the human, and it acts as the demonstrator, whereas the white panda robot on the right acts as the target agent. We now compare against 3 baselines from prior work on this task. The meta-learning baseline uses mammal to learn a policy, whereas the contextual LSTM baseline uses a sequence-to-sequence model with standard attention module in order to learn these pick-and-place tasks. These tasks are then, for reporting purposes, decomposed into reach, pick, and place stages, and success rates are reported for each stage. Note that our model outcompetes all prior work at each stage of the pick-and-place task. Here's a qualitative example of all of the methods picking the Coke can and placing it in the back right. In this example, the LSTM accidentally does the wrong task. And in this example, only our model is able to correctly pick the brown block and place it in the correct bin. In order to understand why our method performs better, we perform a series of ablations. First, we start by ablating the attention architecture. Policies with various network architectures are trained using our losses and our code. The transformer model performs best at the control benchmarks versus all others. Note how it actually outperforms a version of itself trained without attention, which proves that attention is crucial in order to learn a good representation. Finally, we ablate the additional losses in order to understand how our losses are changing things. We train versions of our model without the inverse loss, without the point loss, and without data augmentation. While all achieve the same behavior cloning loss, the inverse model proves to be crucial for control. In particular, look at the blue bar over here. That's the model without the inverse loss, and it always performs worse than our full method, which contains all of the losses, which proves the inverse loss is crucial for control. In conclusion, our method substantially outperforms prior work, and indeed can do so even when trained on 1/3 of the training data. The inverse loss proved to be crucial for actually performing control tasks. And overall, this supports our hypothesis that context and attention-driven and dynamic square representations are good for imitation learning. However, we do assume paired robot and human demonstrations, and that's a crutch that should be removed in future work. Thank you.